So so that's why it's still like. Sure. Yes, exactly.
I'm going to switch to the other side today.
Hey, good morning. Welcome to the last day of this workshop. So before beginning today's talks, I just want to make an announcement for the last workshop of this program, which is the workshop on societal considerations. That workshop is soliciting posters, and today is the deadline for submitting posters. So please do pass this message. Okay, so coming back to this workshop, today is the last day. We'll be having two talks today, half a day. First talk will be by Gabriel Farina. He's at CMU and he's a recipient of the Facebook Fellowship, Neuro's Best Paper Award, and really has multiple streams of very exciting work, including first-order-based methods, regret-based methods for equilibrium finding, many interesting statements to make about extensive form games like correlated equilibria and coarse correlated equilibria for extensive form games, etc. Today he's going to talk about no regret learning for general convex games.
Thanks so much for the show. So thanks so much everybody for
being here. So first of all, let me say, like this work was like a collaboration of a lot of people, amazing authors. So kudos to all of them. But without, with that, let me just jump right into the talk. And I want to start maybe by telling you what you can expect from this talk, just like a takeaway, and then we're gonna deep dive into it, kind of like the math behind it. And feel free to like interrupt at any moment if you have any questions. Cool. So a recent line of work has established uncoupled learning dynamics that when all the players employed in a game, they're such that every player's regret after any t repetitions grows only polylogarithmically in t, or t time, or the number of repetitions. And this has implications for equilibrium finding. This leads to some of the fastest known methods to compute equilibrium in large games. However, so far, these results have only been limited to certain classes of games that have structured strategy spaces, mostly normal form games. That's where I think a lot of the research has been driven. There are some results about extensive form games that I will briefly talk about. But I guess the point that I want to make is that many fundamental models in economics and multi-agent systems require going beyond those kind of like simple like normal form, extensive form, game settings, and instead required looking at general convex compact strategy sets. Right, so this kind of like leads to this natural question, which is, can we attain polylogarithmic in time regret per player in general convex and compact strategy sets, while at the same time retaining efficient strategy updates? I mean, you could imagine that if you have a general convex set, maybe you discretize, maybe you find a net, and you convert it into a normal form game, and then you use one of the dynamics that guarantee polylogarithmic regret, but you don't want to do that. That's very expensive. So we want both efficient strategy updates and polylogarithmic time regret for any kind of just like convex strategy set. And I guess like the whole point of what I'm going to talk about today is that actually the answer is yes. So we answered this in positive. And in particular, we give an uncoupled learning algorithm that guarantees logarithmic in T per player regret. And that holds for general convex compact games. And one nice feature of this dynamics also is that, like if it turns out that not everybody is using the same dynamics in the game, then they kind of like gracefully fall back to square root of T, so like sublinear in T regret in that case. Yes?
I wanted to just ask, you don't want to do the nets because it's computationally expensive, or because you would need a couple of dynamics to do it?
Because it would be computationally expensive.
So, but you could do it in an uncoupled way?
Yeah, that's a good question. I think so. I guess it also boils down as to like what is the feedback. Like these dynamics will be in the full feedback. So I guess like like in general, I guess like the bandit case is a little bit I guess like more complicated. But yeah, I would say probably mostly computational. Cool, right? So like I was saying, like we guarantee that if every player is using these dynamics, they can attain logarithmic in T regret per player. In adversarial settings, they fall back to square root of T, so sublinear. Yes.
Do we assume smoothness or?
Right. Yeah, I'll talk about the assumptions. Like we assume concave losses, and like smoothness, smooth gradients, all of that. Right. So you can think of this as, I think there has been a lot of work in online convex optimization, like in the general convex case where you don't assume any structure about the environment, and it's known that you can attain sublinear regret. This is kind of like adding one step, which is if you know that everybody is using the same dynamics, can you achieve better than square root of T? And the answer is you can do logarithmic in T for any convex set. Yes.
Do the players need to know how smooth the game is, or some information about that, or is it?
That's a good question. Yes or no. I mean, like I guess like the way I will present the math assumes that, but then you could imagine some form of kind of like binary search, right? But then there has to be some form of coordination, which I mean, at the same time, you're already assuming when you say everybody's using the same learning dynamics. So you could imagine that part of the dynamics itself is kind of like to do this backtracking, so kind of like join me. Well, also let me, like because this is like for general convex sets, there's a question as to kind of like what kind of like oracle access do you have to the convex set when you do the optimization. So we have two models. If we have access to what we call a local proximal oracle for the set, which you can think of like basically as like a proximal step oracle, then we guarantee that every iteration of these learning dynamics takes log T time, right? So kind of like close to constant almost. If you only have access to a linear optimization oracle, which is less powerful, then we get polynomial in T cost per iteration. And let me also mention that in special cases where prior results apply, our algorithm improves over the state of the art regret bounds, both like either in terms of the dependence on number of iterations or in terms of the dependence on the dimension of the strategy sets, right? So we actually also give nice improvements in the normal form, extensive form cases for some of the dependencies. Cool. Okay, so I guess that gives like the kind of like an overview of what we're going to talk about. So let me also give you some history and context about this problem. It has kind of like a rich history. So first of all, regret minimization clearly is like a celebrated framework that has been central in the development of online learning and multi-agent systems. The idea of regret minimization is that like you say that you've learned in a game, or like you've learned how to play a game. When looking back, every player does not strongly wish that they had played differently. That's what we mean by the player has learned. And I guess regret kind of like encodes this mathematically. And if we kind of like zoom out and we just like try to find reasons to care about regret minimization, I think there's like at least 3 different scenarios. The first one is that, well, like this idea of learning in games is such a natural kind of like idea, and regret is such a natural notion of performance that perhaps you care about regret minimization just like for the sake of it, like it's just like it's a natural model. And the good news clearly is that no regret algorithms that are designed for fully adversarial environments, they guarantee sublinear regret exists. So that's a nice feature. The second reason why you might care about regret minimization is that it might be a good model for the behavior of the system that you're modeling, like maybe an auction, like there's like some results in economics that say that regret minimization might be a good model of your system. But what I want to focus more in this talk is the connection that there exists between learning in games and computation of game theoretic equilibria. Right, it's known that when all the players are regret minimizing, then the kind of like empirical frequency of play converges to a course-correlated equilibrium in multiplayer general sum games. This holds like no matter the number of players, also like general sum. One thing that's to be said about course-correlated equilibria is that the approximation error in particular is tied to the maximum individual regret. We'll talk about this kind of like idea of maximum individual regret soon. And also let me mention that a special case of this kind of like convergence guarantee is that in two-player zero-sum games, in particular, we can use kind of like self-play of no-regret learning dynamics to converge to a Nash equilibrium, right? Which is kind of like important for just like playing games, for example. Right. So I will want to for this talk, I'll mostly focus on this third idea, like the important connections to game theoretic equilibria. And the idea of how that works, again, is that players train against each other in self-play. And currently, these kind of like learning-based methods are the state of the art for large games by far. And they've had remarkable practical success. They're being used in kind of like recent results in AI. You think about poker, but also like recently like Stratego. There's like diplomacy. There's like Hanabi. Like people have been using these actually to play against humans, and they work very well. And like if you squint your eyes, like we're just saying, okay, we care about regret minimization. It's designed to handle full adversarial settings. That's amazing. But then we just say, okay, maybe we care about convergence to like equilibria in self-play. And then if you look at it, self-play learning is far from fully unpredictable adversarial. Like that other agents are trying to learn themselves, right? So perhaps the fully adversarial setting is not kind of like the right model if you actually care about self-play of agents. And this begs the question, like what performance guarantees can be obtained for self-play in general games, right? Like if you can move away from this full adversarial idea and just say, okay, maybe I know that everybody's doing self-play, how fast can you learn? And like the question, I guess, was first looked into by Daskalakis et al. In 2011 for two-player zero-sum matrix games, and since then there has been considerable interest in extending guarantees to more general settings. So let me just mention a few. Jiang et al. And Rakin and Sridharan, they pioneered around 2012, 2013, the framework of optimism or learning with predictable sequences. Serganis, has a NURB Splitable award where they, Serganis et al. Of course, where they crystallized the RVU property, and that in turn enabled dynamics that have t to the 1/4 instead of t to the 1/2 per player regret in convex games, right? So this is for general convex games, t to the 1/4. Chen and Peng recently in 2020 improved the t to the 1/4 to t to the 1/6, but only for two-player games. And then most recently in 2022, so last year, Daskalakis and there's one name, but Daskalakis et al. Shows that, I think that's a wrong reference. There's also Max Fischelson on the paper, but shows that in matrix games, one can achieve polylogarithmic regret, so log to the 4th. So we went from t to the 1/4, t to the 1/6, and then now log to the 4th by using the optimistic multiplicative weights update algorithm. And this is was a breakthrough at the time because it's an exponential improvement over the guarantees that were so far obtained using traditional techniques within the no-regret framework, right? It was polynomial before, and now it's polylogarithmic. I guess I've done some work with some collaborators extending the optimistic multiplicative weights update result by showing that in certain classes of polyhedral games, so not matrix games anymore, but polyhedral games, which includes extensive form games, one can run optimistic multiplicative weights update on the exponentially many vertices of these polyhedral domains in polynomial time, thanks to a kernel trick, and we call this algorithm kernelized optimistic multiplicative weights update. So basically what you can do is you can convert your game to a matrix game fundamentally and still handle it efficiently. and then piggyback on the log to the fourth t regret, kind of like black box reduction. I've done some work with Ioannis and other extending the technique of Daskalakis et al. To swap regret instead of external regret in matrix games. And then most recently, Piduras et al. Proposed learning dynamics that guarantee log t, so not log to the fourth, but log t regret, but only for a subsequence of iterates in matrix games. Right, and so finally, what we show in this paper is again like log t regret for general convex games, right? So if you were like to summarize kind of like the path that led to here, this is what it kind of would look like. So like we started with I guess like Sergans et al. Result, and then there was like optimistic multiplicative weights update recently. These are all for like multiplayer. So I'm like omitting the 2-player only results. For example, like the T216 that was only for 2 players. Cool. All right, let me also mention that we actually have implemented the dynamics. So just to make sure, like that actually, everything looked like the theory predicted. So these are some experimental results. I mean, they're not important for the talk, but I just wanted to show you, like we have a logarithmic axis, x-axis, right? So you see that indeed, like these dynamics kind of like tend to like flatten up as like lines, right? So you have actually log t regret per player, which was kind of like satisfying to see, the practice matching the theory. Cool. Okay, and with that, I guess we can start talking about complex games and how these dynamics are constructed. So first, let me introduce the idea of a complex game, and this will answer also like some of the questions that Theoretic had. So how do we define a complex game? Well, an n-player complex game has 2 components. Well, first of all, it has n players, but then it has 2 things. Like the first property that it has is that every player plays from a convex and compact strategy set, which I will always denote xi. You can think of this as the set of mixed strategies that the player has. For example, like in a normal form game, which is a special case of a convex game, xi would be kind of like the probability simplex over the action, say rock, paper, scissors. Right, so every player plays from a convex and compact strategy set. And then the second thing is that the utility function of every player is continuously differentiable. It is concave, right? So that's the first assumption. So the convex games are also sometimes called concave games. So it's a little bit of a, you can pick. The second property of these utility functions is that they have bounded gradients, right? So the gradients of the utilities of every player cannot explode. And then we assume some Lipschitzness or Lipschitz continuity of the gradient, right? So we assume that basically if you have 2 strategies x prime that are not too far away, then the gradients of the utilities will also not be too far away. So this is all of the technical assumptions that we make about these games, and then the results in this talk will apply to any game that satisfies this. And in particular, now we'll go through like a small list of games that satisfy this. I guess like the less surprising one is normal form games, right? Like like I'm sure we're all familiar with normal form games, but just just in case, a normal form game is a game that looks like rock paper scissors. Fundamentally, everybody has a finite set of actions. Players pick one action, potentially like from a kind of like they randomize the choice. They play the action simultaneously, so there's like no turns, and then depending on the combination of actions, a payoff is given to every player. Right, so we'll call the action set AI for player I, and then when you want to view a normal form game as a convex game, the way you do it is that like the strategy set that every player has in this kind of like convex representation is just the probability simplex spanned by the actions, right? So all the probability distributions over the action set. And the utility of a player is the expectation, right? So it's kind of like this multilinear function that depends on the probability distributions that are played by the players. And like because this function is multilinear, it's easy to see that the gradients of the utility function are bounded by the maximum payoff. And furthermore, the smoothness of the gradient is kind of like for free. This is kind of like a known total variation distance lemma. Cool. So normal form games, kind of like prototypical example of convex games. Extensive form games are another example of convex game. Extensive form games are games that are played in the game tree. So this capture games like poker, go, bridge, basically whatever. Most interaction in the real world can be modeled this way. In particular, extensive form games are able to capture turns, simultaneous moves, stochastic moves. For example, like stochastic move could be, I don't know, like you draw like a card at random, right? So that's kind of like a nature move. And most importantly, they're able to capture imperfect information, which usually, like if you look in the figure, like these kind of like gray boxes have appeared around nodes. So basically, you can kind of like in extensive form games, you can basically just say, oh, like players don't really distinguish between different nodes and they have imperfect information. It turns out that even with imperfect information, extensive form games are convex games. The strategy space of every player is a convex polytope, which is called the sequence form polytope. Right, we'll not talk about the details as to how it's constructed, but it has polynomially many constraints. We know everything about it. Utilities are again multilinear, right? So which means that for free, just like in normal form games, we get smooth gradients and bounded gradients. All of the good properties that we need for this to be effectively a convex game. Okay, let me mention more example of convex games. We have splitable routing games. There, every player has some flow to route from a source to a destination in some undirected graph. Every edge is associated with a latency function that maps kind of like the flow that passes through the edge to some latency. In this case, if you want to see this as a convex game, the strategy set of every player would be all possible ways of splitting flow into paths from source to destination. So this is a convex polytope. And under suitable restrictions on the latency function, then you can also show that these games satisfy the convex game definition, so like bounded smooth gradients. I guess like the last game or like class of games that I will talk about is Chrono competition games. Their players are actually firms. Every firm or player, I decide some quantity of some good to produce from some interval, for example. A cost function for every player assigns a production cost to the given quantity that the player has selected, and then the price of the good is determined by the joint choice of quantity. So that is instead determined by how much quantity all the players have picked. And the utility of player I or firm I is defined as this simple function, like it's like the production cost basically minus the price at which you can sell the good. And there's like an important case in Chrono competition games, which is concave and smooth function UIs, which fundamentally brings down this problem to a convex game, right? So here you would have the strategy sets of every players like intervals, and then you have concave functions that have smooth bounded gradients. Right, so I guess we talked about this 4 classes of games: normal form, extensive form. I guess we talked about splitable routing games. We talked about Chrono competitions. Hopefully, at this point, you're convinced that like convex games are kind of like a meaningful class of games that we care about. Okay, briefly before going to kind of like more of the core of the math as to how these dynamics work, let me just like fix some ideas about the learning setup in convex games. First of all, like as always with the minimization, we're talking about repeated interactions. At every times t, every player outputs a strategy from their set. So we will always denote strategies with x, and the subscript will always be the player. The superscript in parentheses will always be time. And then after every player has output their strategies at time t, then everybody observes the gradient of their own utility. So this goes back to Nika's question, right? Like this will be the kind of like what is called the kind of full information feedback model. So in particular, like the utility vector of player I is like the gradient of their own utility given the choice of strategies for all the players. The gradient only with respect to, of course, the strategy of the player I. Cool. And then the canonical measure of performance of each player is regret, right? So I've been talking about regret this whole time. So like this is like the definition of regret that we're going to use, like standard definition of regret. Basically, we just look at, like if we could go back in time and just like pick the best fixed strategy X star in hindsight, what is the difference between the utility that would have achieved minus, whatever XIT has accumulated over time. Cool. Any question about this is like the last slide for the kind of like the setting or the setup. So if you have like any question before we delve into kind of like dynamics. All right, so I guess with that, let me tell you philosophically how you can achieve, this log T regret, and then we'll talk about how to actually implement that plan. But I'll talk about, I guess, like three things. The first thing is I want to talk a little bit about really what RVU bounds enable and what they don't. In particular, I guess like the spoiler is that RVU bounds are very good when you care about the sum of the player's regrets, like the social regret, but no guarantees, or at least I have like 3 question marks, because at least I don't know any guarantees, but maybe there is something that could be said. But I think currently that's kind of like a question on individual regret. Yes.
Sorry, what is the full form of RVU again?
Oh, we'll talk about okay. So RVU, just like historically, that is I guess I talked about it when it came to the work by Serganis et al. Right, so like in the 2015 New York paper that they have, where they are kind of like the first to give like this Tilde 1/4 like dynamics in self-play, like the 1/4 regret dynamics in self-play. They do it through this idea of like the RVU regret bounds, and we'll talk about.
My question is, RVU stands for what?
Oh, it means regret bounded by variation in utilities, but actually it's a little bit more than that. So it's more than the variation in utilities. We'll talk about it, but yeah. But you can think of it as just like type of like predictive regret, kind of like guarantee. Cool, right? So basically, like the first thing was what RVU bounds enable and what they don't. Part 2 is what would be enough then to enable this conversion from constant social to ideally constant individual regret guarantees. We'll not quite get to constant, but like we'll talk about what could get there. And then like after talking about all this, hopefully this will like give like a good blueprint for what's to come. So let me start with RVU bounds and the idea of social regret. So an RVU bound is a regret statement of an algorithm that looks like this roughly, right? And I will always use the less than with the kind of like approx thing to just mean that I'm kind of like removing constants that are kind of like irrelevant for the discussion, and that would just kind of like clutter the math, but not really the idea. So fundamentally, what it means is that if we have a learning rate eta, then the regret roughly looks like you have a constant over eta, right? So if eta is too small, that's not good, because the regret then, like the regret bound is very high. Plus the learning rate times basically the amount of variation that has happened in the utilities of the player, right? So that's why it's called the regret bounded by variation in utility, right? So like the variation of utility is like the second part. And then we have minus the inverse of the step size times how much variation has happened in the utilities, sorry, in the strategies of the player, right? So it's like regret bounded by variation of utilities minus variation of strategies, if you want, right? And one thing that's interesting is that last term, if eta is very small, like if the learning rate is small, is very negative potentially, right? So it's kind of like a nice feature. So let me mention this, like like RVU type bounds are very powerful. And in fact, the fact that you can even write statements like that immediately implies that the social regret, which means the sum of regrettable players, is at most a constant independent of time. And the idea for that is pretty simple. This is kind of like basically what happened in the paper by Serganis in 2015. Like if you use the smoothness of the utilities, then the middle sum can be bounded, like by kind of like the variation of the utility, because like UIT minus 1 basically is the difference in utility that has happened given that the strategies were XT and XT minus 1, right? So the variation that has happened in the utility, because we assume Lipschitz smoothness of the utility gradients, is upper bounded by the sum on the right. And if you plug that into the middle term and then you sum over all the regrets, you end up with something that looks like, well, we are counting the 1 over eta, the first term in the RVU bound n times, because once per player. Then we are counting n times the middle term. And then for every player, we have that minus 1 over eta times the sum of the variation. So basically, this kind of like sum of variation of strategies you can collect. And then you have this term n eta L squared minus 1 over eta in front of it. And then, like we said, like if eta is small, this factor in front can be negative, right? So you can just completely throw away like the social variation of strategy, or what is called like the social squared path length, and you end up with this less than or equal n over eta, which is a constant that does not depend on time. Okay, so this is kind of like the big idea behind, I guess, or like one of the big ideas behind the 2015 paper by Serganis. Okay, any question about general kind of like idea. Basically, like RVU bound, I guess, implies constant social regret. This is kind of like the message of this slide. But like that social regret, what can be said about individual regret? And unfortunately, convergence to course-correlated equilibria in multiplayer games is driven not by the social regret, but the maximum individual regret. Right? So the fact that we have a guarantee that says, oh, the sum of the regret is at most constant might tell us nothing about the individual regret. And if this sounds like weird at this point, I think one thing that can always like confuse is that regret can be negative, and in fact can be very negative. Like if you have this predictive learning dynamics, you might have, okay, that the sum of the regrets is constant, like it's most a constant, but then one player has learned so well that the regret is so negative, and some other player might be kind of just like being left behind, and so they have a huge regret. And then like the sum maybe is still small, but then you're not converging to a course-correlated equilibrium, right? So that's why social regret and individual regret are very different, and they require different techniques. At this point, you might be wondering, like, what do RVU bounds tell us about individual regret? And they tell us two things. The first thing is that, like RVU bounds are still valid. And in particular, if you ignore the third term, like the -1 over eta sum of the distances, and then you bound the middle term like we did before, this expression is still valid for the regret of player I. And what this means immediately is that if we somehow knew that the social square path length, like basically the term on the right, was small, like was it say like at most a constant, then we would be done, right? Then the regret of every player would be at most constant, right? So effectively, like the RVU bound, what it does is that it hints in the direction that maybe the thing that you have to bound the regret is how much movement the players, just like can achieve. On the other hand, like if you sum the regret, this expression is still valid. Right, like so for a constant learning rate, you can still write this thing about the social regret. This is like what we had in the previous slide, right? So we said, oh, if you throw away like the right term, this is at most a constant. But if we don't throw away the right term, the big idea is that if we somehow knew that every player's regret is non-negative, then from the second equality, you would have that the social path length is at most just like n over eta. And that is at most constant with respect to time. And so we could plug it back into the first equality and have constant individual regret. Alternatively, another way of saying this is that we know that the sum of the regrets is at most constant. If we know that the regrets also happen to be non-negative, then, of course, every regret also has to be constant.
So basically, what happened from the first to the second?
I summed, right. So the second inequality does not come from the first, but it comes from the RVU bound. Right, I'm just saying the RVU bound, if you look at each individual player, can tell us the top thing. And if you look at the sum, can tell us the other thing, right? So I guess like the idea is that if you know that the sum of the regrets is non-negative, then from there, you would be able to kind of like switch kind of like the social square path length to the left-hand side, say that that is constant, and then plug it back into the first equality. Right. So again, like I guess like philosophically, like the main takeaway is maybe like you care about like if only we knew like the regrets were non-negative, or the sum of the regrets would be non-negative. Either way, we would have constant regret per player. Right, which leads to the main question, which is can we somehow ensure non-negativity of player regrets while at the same time not losing the RVU bound? Like if this is kind of like where this kind of like research started, like this idea that if somehow we can ensure the negativity of player regrets and not lose the RVU bound, then we're done. Okay, so now I guess like I'll talk a little bit about the way we achieve this kind of like non-negativity of regrets. Well, first of all, to not lose the RVU bound, perhaps it's not surprising that our regrets are like our dynamics are based on optimistic FTRL, which is one of the two classes of algorithms that are known to have RVU bounds. The other one being optimistic mirror descent. Right, so we use optimistic, follow the regularized leader, but with three important twists to kind of like ensure this non-negativity of the regrets. The first twist is we use some lifting, and what it means, like what that means is that optimistic follow the regularized leader will not operate on the set of strategies of the player, but rather on some lifted set, math cal, like kind of like cal X with a tilde. right? So tilde will always refer to lifted quantities. Of course, because now we're operating in this lifted space, then feedback for the learning procedure needs to also be lifted to this x tilde before the iterates can be produced, and I'll talk about how that works. So that's like the first twist. The second twist is that we use a very specific type of regularization, which is logarithmic regularization. Right, and what that means is that for the regularized leader will, which is regularized, will use kind of like this log regularizer. And one of the, I guess, like interesting things that happens is that this log regularizer is not a log barrier for the set, right? So we use a log regularizer that is not a log barrier, which is kind of like puts us kind of like a little bit outside of, I guess, like what people usually do. The other thing is that lifting, like the idea of lifting is kind of like very used in other contexts, but as far as I am aware, it's not really used to ensure non-negativity of regret. So I feel like that's also kind of like a different thing. So anyway, so lifting log regularization, the third twist that we introduce is this idea of normalization. So because we're now operating on the lifted space, we somehow have to, at the end of the day, like go back to strategies for the original space, and we do that through normalization. So, just like we have like this kind of like pipeline where utilities come into the regret minimizer, they're first lifted, so they become utilities. Then they're fed into this optimistic for the regularized leader that is instantiated with a log regularizer. This produces lifted strategies that are then normalized to go back into real strategies. Okay, so from now on, I'll drop all the subscripts that relate to players. We'll only be looking at regret for one player. So, like you can imagine that all the quantities are per player. Without loss of generality, we assume that the set of strategies of the player has already been shifted so that like all the entries are non-negative. Right, this will be important for the log regularizer because like log of negative numbers is not defined. So right, so we first shift the set. This can be done without loss of generality, of course. Given any vector x or like a strategy x in the set of strategies, or in fact really like any vector, we don't know the kind of like indexing into the vector with square brackets. Otherwise, there's like too many subscripts and superscripts, right? So square brackets mean like indexing into the vector. And then we always assume that the strategy set of a player never kind of like flat with like one coordinate always 0. Because I mean, if that was the case, you could always drop it without loss of generality. And again, this would pose problems when you have log of 0, right? So we don't want that. All right, perfect. So let's just start from the lifting. So what does lifting of the strategy set mean? Well, it means that we start from a strategy set, which you can imagine is like in RD. And now we construct a set x tilde, which is in, like RD plus 1. And the way we do it is that basically we take the set, we lift it, and then we take this kind of like truncated conical, if you want, right? So basically we took the set, we lifted so that we added one, extra coordinate, which is always 1, and then we took kind of like the interval 0, 1 times the set. Okay, so I guess pictorially, if you want to think about it, it's kind of like this figure. Cool. So this is lifting. Of course, like we said, like if we lift your set of strategies, then you also have to have a plan for how to lift the utilities or the feedback that you give to the learning algorithm. And like the lifting of the strategies, the lifting of the utilities given a utility UT is defined this way, right? So basically we take UT and then on top we stack the expected, like the inner product between the utility and the last output strategy with a minus sign. And I guess like the only important thing, like as to why we do this, is that we can guarantee in particular that the inner product between like the lifted utility and the kind of like lifted strategy, like where you put the 1 and then the past strategy you played is always 0. So like those two vectors are orthogonal. So that tells us like the lifted utilities, log regularization. So the logarithmic regularizer is like exactly what you would imagine, right? So basically you just take minus log of all the coordinates. It is a self-concordant function, but it's not a barrier for x tilde. So we'll come back to that. And then.
So just clarification, what do you mean it's not a barrier? What does it mean?
It just means that basically like the gradients of the log regularizer don't go to infinity on the boundary of your lifted set. Right. So normally when you use like the kind of like the log regularizer, it happens to be kind of like a barrier for your set, so that then when you take proximal steps, you never go out. But here we need to be careful. Cool. And then normalization, what it means is that after we produce a lifted strategy, which might be like a point kind of like in the middle of this cone of lifted strategies, we need to kind of like project it back or renormalize it into a real strategy for the original set, and we do that by division. So basically, we just kind of like draw a line that connects the point until we reach this kind of like plane at lambda is equal to 1. Okay, perfect. So with that, I mean, the algorithm itself is incredibly simple, right? So we have basically, once, like if you look at line 5, we observe the utility, we lift it on line 6, we keep the Tilde that is needed for optimistic for the regularized leader on line 7, and then on line 3, we produce the iterate using the usual FTRL step, and then in line 4, we just normalize it. So nothing weird is going on. So why does this work? Well, interestingly, I think lifting makes regret non-negative. I think this is like basically probably like the biggest takeaway. So in particular, like if you have regret on the original strategy space and the regret on the lifted space, right, which are kind of just like writing the definition of regret, it turns out that there is a strong relationship between the two. And again, like remember that, like in the two formulas, like I'm assuming that, of course, like the utility is like the lifted of the utilities, and XT is like normalization, right? So there's like, direct correspondence between the different terms, right? There is a strong relationship between regret and regret tilde. And in particular, it turns out that regret tilde is exactly equal to the max between 0 and regret. Right, so this has two consequences. The first thing is that regret is upper bounded by regret tilde, right? The regret tilde being the regret in the lifted space, which means that any algorithm that guarantees small regret in the lifted space automatically guarantees small regret on the original space. And the second thing is, of course, like that result immediately implies that regret tilde is not negative. Okay, so at this point you might be saying, okay, like regret tilde is not negative, then we're done. We can just use the idea that we had before, but this is far from done, right? And like we have established a negative regret in the lifted space, but we cannot invoke the result we mentioned earlier. And the reason is that the utilities in the lifted space are not Lipschitz continuous with respect to the strategies in the lifted space. In particular, what we have is that the utility in the lifted space are Lipschitz continuous in the strategy in the original space. And when the lambdas are very small, like those fractions can vary a lot. So if you have that basically like your dynamics in the lifted space take you very close to the origin, then you don't really know how to bound the kind of like the utilities in the variation of the utilities in the way that you need. Okay, so it just because we have that the lifted regret is not negative, we're far from done. And this is exactly where the choice of using the log regularizer comes in. Basically, like the log regularizer is chosen exactly so that we can kind of like transfer smoothness in the lifted space to the original space. And in particular, like log regularizer, you can prove that enables this idea, which is multiplicative stability. So multiplicative stability, what it means is that the iterates that are produced in the lifted space guarantee that across successive iterations, the ratio between the components of the strategies vary by like relatively by at most epsilon. Sorry, by most eta. Right, so you have that the ratio between the lambdas and the y's, which are kind of like the lifted strategies, is bounded between 1 minus eta and 1 plus eta at every time t. And like this comes from the fact that like it's known that dynamics are locally stable, which means that in particular they're stable with respect to the Hessian of the regularizer. And we chose the log regularizer exactly because then the Hessian is kind of like nicely 1 over the square of the components. So when you plug the Hessian back into the local stability condition, then you end up with something that looks exactly like multiplicative stability. So multiplicative stability basically comes from having chosen the log regularizer so that the Hessian has this particular structure, and then knowing that follow the regularized leader is locally stable, not just stable.
This kind of local stability also
right. I strongly suspect that you could do this whole paper like with mirror descent. So often what happens between mirror descent and follow the regularized leader, at least with Legendre regularizers, is that like the iterates are the same. But in this case, because we don't really have a barrier, then we cannot really just say, oh, this would be exactly the same iterates produced by mirror descent. So I think you would need to kind of like touch on the proofs a little bit to make it work. But I would be surprised if this didn't work for mirror descent. I guess we just picked follow the regularized leader just I don't know, I guess like, I don't know, it seemed like easier to make it work directly. Cool. Right, so multiplicative stability, like we said, enables us to transfer smoothness in the lifted space, from the original space, right? So we had that in the lifted space utilities were smooth with respect to the strategies in the original space, but in particular, like because of the multiplicative stability, then we can, just like there's basically not much difference between smoothness in the original and in the lifted space, basically. Right, so in particular, we can establish an RVU bound for regret tilde, which is non-negative, that relates to quantities in the original space instead of the lifted space. And from there, like we said, at this point, we can, like carry out the plan that we talked about, right? So at this point, we have bounded social square path length because the regret tilde is non-negative. And in turn, because we know that regret tilde also bounds the regret, then we have that the regret is the most logarithmic integral. Right, so these are kind of like all the the different tools that are used. Again, like we have the lifting to make the regret non-negative and multiplicative stability to transfer smoothness guarantees from the original to the lifted space. And this is what the final regret bound looks like, right? So basically, if the step size is small enough, whether small enough means like a constant that potentially might depend on the the smoothness, like the Lipschitz constant, the number of players, the size of the strategy set. But anyway, basically, like anything, like if eta is small enough in a way that is time independent, but only game dependent, then you can guarantee that the regret of every player is at most a constant times log t, where again, the constant does not depend in any way on like time on the side of the game. Right, so once again, like this is what like the different regret bounds look like, right? Like we get this log t. I'll like if you look carefully in the regret bounds, like you will see that like for example, like log t is better than clear like log to the fourth t and to the 1/4, but the dependence on some of the other game parameters is not as good as it could be. For example, like in normal form games, like we have, for example, that like our dynamics have a d factor, whereas if you look at optimistic multiplicative weight of data, like the second line, we have a log d factor, right? So I think it's like I'll talk about like kind of like questions as to how can we maybe improve this for special cases so that we end up also having like good dependence on, say, the dimension of the set compared to other methods. All right, cool. So the last thing I want to talk about is some details about implementation and iteration complexity, because so far, like we've just said, oh, okay, we have like these proximal steps that we take in fold regularized leader, and then they have multiplicative stability, and we get logarithmic regret. But like this assumption that we can make, that we can actually compute these proximal steps is not obvious, especially for a convex compact set X for which maybe we don't know anything. But also, like there are possible complications here. The first thing is that the gradients of the log regularizers diverge close to kind of like, if one entry is close to 0, then your log of 0 is like very big in absolute value. I guess log of something close to 0 is very big in absolute value. The log regularizer is not a barrier function, which means that I guess I keep coming back to this thing, but like what it means is that you have to be careful about kind of like the boundary all of a sudden, like just say, oh, just like I take a step, and as long as it's like eta is small enough, I'm always inside, like you would do, for example, like with like Newton's method with a barrier. But I think the biggest issue is what happens to the guarantees, especially like of multiplicative stability, if the solutions to this optimization problem are only approximated. So like say that we're only able to find a solution that is close, like in the sense of like the norm of our solution to the correct solution is small. Well, that will be not enough, because the whole point of doing this optimistic FTRL with log regularizer is that we need to guarantee multiplicative stability of the iterates that are produced over time, and that is known to hold for the exact solutions. But now if you have kind of like a additive perturbation around that might completely destroy all the arguments, right? So this fact that, like we cannot just like settle for an additive error bound on the kind of like on how close we are to the exact solution is a problem, right? Because then, like when you combine these three things, it's not, I think, obvious, like how do you actually compute this approximately? right? So like I said, we cannot seek additive error guarantees. In particular, what we need to do is we need to, seek relative or multiplicative error guarantees. So basically, we need in turn to have that kind of like the approximate solution, which is the ones at the top, like lambda and yt, compared to the exact solution, which are like the ones with the star, are within a factor epsilon t, like multiplicatively, like relatively from each other. And once you have that, it's easy to see that as long as the relative approximation error is of order 1 over t, then the degradation that you have from not using exact solutions to your proximal step is at most constant. And can we achieve all of this? And it turns out, actually, like I kind of like set up for this for being complicated. But one of the things that surprised us is that it turns out that we can achieve all of these properties efficiently by using a modification of Newton's method that enables quadratic convergence. And like that, compared to like, for example, like the usual Newton method, like holds even if our regularizer is not a self-concordant barrier, right? So actually, it took some time to finally complete this last piece because there were like so many obstacles. But actually, it's surprisingly simple. It turns out that there exist modifications of Newton method that guarantee that we can achieve all of this even for this log regularizer, which is not a barrier. And in particular, we proposed two ways of solving the issue. The one way is through what we call a local proximal oracle. So what it means is that basically in the lifted space, we need to be able to solve this kind of like quadratic optimization problems, right? So basically, it's a proximal step where we have a generic center W tilde, we get a generic gradient G tilde, and then we need to kind of like compute the argmin of this function, which as usual of proximal steps has a linear part, so G tilde transpose X tilde, and then it also has a quadratic part, which is plus 1/2 of this quadratic term. But the reason why this is like a local proximal oracle instead of a proximal oracle is that the quadratic term is contains a positive definite matrix, which is the Hessian of the regularizer in W tilde, right? So depending on the center at which you're trying to evaluate the proximal step, you might have the quadratic term changes, right? So it's kind of like a dynamic quadratic term, right? More, I guess, like concretely, basically you have to, like, as long as you're able to compute solution on your lifted set of convex, like strictly convex, or like strongly convex problems of the form in the second line of this form, then what we show is that we can basically, in log t time per iteration, you can actually compute these approximate solutions that you need for the proximal step. So in particular, in normal form games and extensive form games, we actually showed that this local proximal oracle can be constructed, right? So we actually have, just like constructed one, did like the experiments that you saw earlier that we're using that, that oracle. And of course, like, one would need to check that this oracle can be, when I say constructed, I mean constructed in polynomial time, right? So like you can find an exact solution of this local proximal problem, like this kind of like linear plus quadratic term in normal form and extensive form strategy spaces in polynomial time, right? And when we do that, we can then invoke, like the idea of like using Newton with local proximal oracles. I mean, that's not ours. Like we learned from this other paper by Trandin. And basically what it turns out is that as long as you have that local proximal oracle, then you can compute like good approximate solutions, so like with relative epsilon approximation to your FTRL problem using log 1 over approximation operations and log 1 over approximation calls to local proximal oracles, right? So this explains the log t per iteration complexity that I promised for these learning dynamics that we've been proposing. Okay, so last thing. So what if we do not know how to construct a local proximal oracle for set X, though, right? Like you could imagine that, I mean, as I said, for normal form and extensive form games, we know how to construct those proximal oracles. For intervals, it would be easy, but maybe your favorite convex game has a set of strategies X for which you don't know how to construct a proximal oracle. Well, the good news is that you can implement the method correctly, which means like you can guarantee this kind of like relative approximation to the steps of follow the regularized leader, even only if you have linear optimization oracles, which means like if the only thing that you can do is how to maximize linear functions on your set of strategies X, then that is enough to still retain log T guarantees, even when you factor in the approximation guarantee, the approximation of the like follow the regularized leader steps. And in particular, we use another tool. This one's from like a recent paper by Liu et al. That is called Frank-Wolf-Newton, and effectively, you know, like the guarantees look like this. So if you want to achieve relative epsilon approximation for your FTRL problem, and you only have access to a linear optimization oracle, then as long as you are willing to pay polynomial in 1/epsilon operations and polynomial in 1/epsilon calls to the linear optimization oracle, then you're good.
So just to compare this, what you had in previous slide with OMW, so they have polarization complexity O of B, and yours is log T times poly D. So
yes.
log T is like a constant, this D is poly D. Right? That's the comparison.
Right. Exactly. Yeah. Exactly. Right. So I'll talk a little bit about exactly like comparison with OMW and whether these dynamics can be improved. Like if you know that you're, for example, dealing with a normal form game in particular, like can you take the same ideas of lifting and a negative regret, but package it in a way that's normal form game specific, so that you can like somehow gain this like log D cost, for example, like term in the dependence in the regret, as opposed to poly D, and also like more favorable complexity per iteration.
Poly D is what exactly?
So what was that?
So what is the poly D?
For normal form games, these would be the number of actions.
No, the poly D, what exactly is the poly D?
What is, I think it's like D to the 3. Yeah, it's not something crazy like D to the 75 or something, but and we've been implementing these in relatively large games, so this thing can scale to some extent, but yeah, like definitely compared to multiplicative weights. I mean, multiplicative weights is also like way easier to implement, right? You just have to do like exponentiation, whereas here you have like all this trickiness of the local proximal Newton and all of that. But anyway, so like zooming out, what are the important takeaway messages? So the first thing is that we developed this learning dynamics that are uncoupled, such that when all players in a general convex game employ these dynamics, the regret of each player grows only logarithmically in time. This significantly extends and strengthens the scope of all player work. And one of the nice features also of this, which I have not talked about, but sorry, before that, like also our uncoupled learning dynamics can be efficiently implemented using, for example, a proximal oracle for the underlying feasible set. We showed log T. One other feature that is nice about these dynamics also is that, and I've not talked about this, but is the fact that you can modify them slightly so that they gracefully can like fall back on giving say square root of T regret if they figure out that the environment actually is adversarial and not everybody's doing self-play, right? So you can use them as kind of like drop-in learning algorithms for whatever like setting you're looking at, and they will fall back naturally. There are some open questions. I guess like this is kind of like a very active area of research, and of course, like what we know is still like a fraction of what we would want to know. But let me just like note some questions here. So in the special case of normal form games, the dependence on the dimension of our dynamics is linear as opposed to logarithmic, right? Like in optimistic multiplicative weights. So like a natural question is, like, can we improve that? For example, like if we looked at, like if we knew that we were only working on normal form games, can we somehow just like leverage that in our dynamics? The other question that again relates to optimistic multiplicative weights update is, there they use entropy regularization, which is kind of like an easier tool to work with. Unfortunately, the Hessian of entropy regularization is not powerful enough to achieve multiplicative stability, or at least we don't know how to do it in like for general sets. So a question, like a natural question is, can entropy regularization be incorporated into our framework as opposed to log regularization, which, like as you can imagine, like log regularization, because it, like even just like the range of the log function can be infinity, close to the boundary, it poses a lot of like other problems. So, like can we somehow maybe switch to entropy regularization?
Like implementation difficulties could be like lessened.
Right, the implementation difficulty of entropic would be less. Yeah, exactly. Right, like also because at least like for normal form games, If you use entropy, the proximal steps have a closed form solution that is very easy to compute, for example. For the log regularizer, you would need to do this kind of like Newton method, basically.
Then what's missing is the stability, you said.
What's missing? Yeah. So if you try to use entropy regularization in the argument, like in kind of like the structure of the regret analysis that I showed you, like the place where things break is the multiplicative stability, because the multiplicative stability depended on the Hessian.
The lifted strategies lambda.
Right. Like the multiplicative stability in the lifted space, like of the lifted strategies, right? Like the way we obtained that multiplicative stability guarantee was because we know that follow the regularized leader is it's kind of like stable in local norm, and the local norm induced by the log regularizer is like the diagonal of 1 over x squared. So when you just kind of like expand this definition, you basically end up with squares from the top that depend kind of like on the strategy variation, and then at the bottom, which depend on the Hessian of the regularizer. And because you have square and square, you can just kind of like put them together and good things happen. But if you use entropy regularization, the Hessian is not 1 over xi squared, but it's rather 1 over xi. Right, so you don't have the square at the denominator, and this, you know, like at this point, you don't know exactly what to do. Cool, right? So I guess like, yeah, that was like another question, like, can we use entropy regularization? Another question is, what can be said about different types of oracles? One natural question is, you know, can we use separation oracles instead of like local proximal oracles or linear optimization oracles? And if so, it seems like the ellipsoid algorithm could be like, at least theoretically, like kind of like a natural choice then to implement the proximal steps that you need for FTRL in like in our dynamics. And then kind of like very fundamental questions, you know, like, is O log T per player really the best that we can do in convex games or in all convex games? Or, you know, like, what is there like a matching lower bound? And beyond that, you know, like, if we go beyond external regret, like what happens in swap regret, say you want to converge to correlated equilibria in normal form games, or what happens to 5 regret in extensive form games, like say maybe you want to converge to extensive form correlated equilibria. So we're doing some work in that direction. Some of the ideas here can be generalized for 5 regret, which in turn also, you know, like has a specialization implies results for swap regret. So there is something that can be said here, but I feel like definitely we've not seen the end of this. You know, it would be very nice if you know, somebody could develop like nice, you know, just like simple to implement no-regret dynamics, or maybe like it turns out that optimistic multiplicative weights already is the dynamic, all the dynamics that we need. And just like we're just like one regret analysis away from just like getting where we want to get. Anyway, so that's it. You know, happy to take any questions, and you know, like if you prefer, I'm also very happy to talk more via email.
I guess. Yes.
Any comments on this?